אבל ההסתייגות היא שתשתמשו בהם כדי להתאמן, אבל הם יותר קשים ממה שהם
מה מדובר? לא הבנתי.
על המבחנים.
שאתה...
הפורמט יהיה דומה, הסגנון, שאלות 1 ו-2 יהיו דומות בסגנון, השאלה 3, אני צריכה עוד לחשוב מה לעשות עם זה. יכול להיות שאני אצטרך לשנות קצת את הפורמט.
60 נקודות.
אבל, מה? לא, אז אני לא אשאל אתכם על חומר שאתם לא שלטו בו, לא אמורים לשלוט בו, שלא באשמתכם, אז יהיה לכם כן בתרגילי בית, שאלות על כל חומר שצריך למבחן. אז השיעורי בית, לעשות שיעורי בית זה הכנה טובה, וגם יהיה שיעור חזרה. יש שיעור חזרה למבחן, לפני המבחן. Okay, let's start. Last time we introduced the concept of the half integral. And the subject of today is to extend this idea to many body systems. So let me first remind you what I did last week. We considered a single particle with which classically is described by a coordinate q and momentum p. And we asked the question how to calculate its propagator. Namely, we prepare the particle at some position qi, and we asked the question, what is the amplitude for arriving to point qf after some capital T time? So we showed that instead of solving the time-dependent Schrödinger equation and then finding explicitly the wave function as a function of t, we express this propagator as a multidimensional integral, which is reduces the problem to calculating integrals, and inside the integrals, everything, all the quantities are regular numbers. They are no longer operators, and that's, in a sense, a simplification. Okay? And we also interpreted the result as a calculation where we assume that the particle traveling between 2 points as a quantum mechanical particle always has uncertainty of its position and momentum in such a way that in principle the particle is allowed to explore all the possible trajectories between 2 points, but the interference between them is what gives the final result for the probability to arrive at the point qf, and it is dictated by the Hamiltonian. So let me write down the result that we got. So first of all, we calculated the time dependence or time evolution. And this is all for a single particle. And today what we're going to do is to extend it to a many particle problem. Now there's another thing that I want to put here on the board for the rest of the lecture. We are going to adopt units where h bar and k Boltzmann are 1. Why is it useful? Because everything that has dimensions of energy, frequency, and degrees Kelvin are all units of the same thing. Okay, so energy is measured in units of joule, if you like, but also in terms of units of frequency and degrees Kelvin. Okay, that's what it means. And then we don't have to carry them around, although you have to keep in mind that when you finally get the result, you have to convert it to real units. Okay, so first of all, we calculated the propagator. And this is what we call G of Qi, Qf t. So it's a function of three variables: the initial and final coordinate and the time of evolution between them. And it is defined as the matrix element of the time evolution operator between Qi and Qf. This is a definition, okay, where H is is some Hamiltonian with some potential. Yes?
It's QFJ or it's
sorry, this is
no,
Q,
no.
not sorry, not X. It's Q, of course.
I mean in G.
What?
In G, it's
Qi, Qf, and T.
Okay.
This is a double column. Sorry, it's a double column. Okay. This is how the convention of how you write it, okay? So, so what we showed last time is, I'm just writing the final result, that we can write it as a functional integral over all possible trajectories which satisfy that at time equals 0, Q equals Qi, and at time equals T, it equals Qf of e to the I s. So s is a functional of Q and Q dot. And it is given by, and the S is the action, integral from 0 to capital T of the Lagrangian where the Lagrangian is 1/2 m q dot square minus v of q. Okay, just the usual definition of the Lagrangian. This is for the time-dependent problem. And a second thing we showed that there is a mathematically equivalent problem for a particle undergoing dynamics under the same Hamiltonian. We can also ask a very different question. Instead of calculating the time evolution and the propagator, we look at a static problem, and we ask the question of what is the statistical mechanics, what is the thermodynamic state of the particle under a given temperature, okay? And the quantity that we want to calculate in this case, so this is now a stat mech problem. And it is a bit funny to do a StatMech problem for a single particle, but you know, if we have many particles of which are identical, then sampling a single particle over a long time is equivalent in some way to looking at an ensemble of particles. So there is the Liouville theorem that I'm sure you heard of, you learned in your StatMech problem, but in any case, usually we are doing StatMech for many particles, and I'm going to start doing that today, but to get the technique, we start from a single particle, okay? And we'll see that it's very easy to extend it to many bodies. But first, why am I doing it for a single particle? First, because to solve this problem, I don't need to solve it again. I just copy and paste from the time-dependent problem and change variables. So what is the question that we ask in a StatMech problem? First of all, we want to compute a partition function. Partition function, the canonical or the grand canonical partition function is a quantity that once you know it, as a function of temperature or chemical potential, you can derive all the thermodynamic quantities, right? You can derive the entropy, the internal energy, you can compute the pressure and compressibility and whatever, any specific heat, okay? So this is the key to all thermodynamic quantities, and the definition is a trace of the operator e to the minus beta h, where the trace means summing over all quantum states, and usually to do that calculation explicitly, you adapt some state, some complete set of states. I denote it by an index n or alpha. Or today we use alpha for something else, so I don't want to confuse. Let's call it n. And this is generally what you have to do. This is the definition of a trace, okay? You write this operator as a matrix in some basis, and you sum over the diagonal elements, and that's a trace, okay? So, in particular, if we then adopt the complete set of states of the particle to be a coordinate q, this becomes an integral of the matrix elements of e to the minus beta h in the state q. And here is where we are adapting the results of this calculation, because of the mathematical similarity between this matrix element and the propagator, we basically see that this thing is nothing but the propagator if we change variable so that qi and qf are just the same q, and what before was t will now become minus I beta, okay? Okay, so beta serves as an imaginary time, and you can just adapting the result that we already got for the dynamical, for the time-dependent problem, we know how to write it, So we therefore can write the partition function as follows. Once again, it's an integration over all trajectories, and notice that we also integrate over this q, this last q. Okay, it's one more integral, but it's actually, this is already a multidimensional integral over all the possible q of taus, which satisfy, what do they satisfy? Like here, they satisfy some boundary conditions in time, that the initial state is qi and the final is qf, but this propagator qi equals qf, and we allow q to be anything, right? We integrate over all q, but the constraint is that it has to satisfy periodic boundary condition in this time direction, this imaginary time direction. And then when we put it in the exponent, once again, because it's an imaginary time, we get a real exponent, not an imaginary exponent. It looks like e to the minus s of q and my eraser. Of q and time derivative d tau q. Okay, and this is given by half m d tau q square plus v of q. So notice that there's no opposite sign between kinetic and potential energy, and that the reason is that this is an imaginary time, so the square of the time derivative changes sign. This is called an Euclidean action, okay? And that's it, that's the result. And I forgot to define the differential is, okay, it's the limit of a product of many, many differential. I'm not writing it explicitly, but conceptually, it is just an integration over all possible trajectories that in this case just satisfy periodic boundary condition. So if you like, it's the way to think of it is that we have some coordinate q, and we also have a time axis, the imaginary time axis. But the imaginary time axis is actually repeating itself. I mean, this is the tau. This is the tau axis. Okay. So tau runs from 0 to beta, where this point is both 0 and beta, the final value of tau. But the particle returns to itself after time beta, okay? So if you like to, you can think of that this tau, sorry, this is wrong. What I wrote here is wrong. This is the Lagrangian. Sorry. Sorry about that. Yeah, here I missed one equation, sorry. This is the Lagrangian, but which is half m d tau q square plus v of q. Okay, so it's an integral over tau from 0 to beta, something that includes a dependence on the tau derivative of Q, and there is a potential energy, and it assumes that this, you can think of this tau, this imaginary time, as if there is another space axis, in a sense. There is one space axis, which is Q, okay, the coordinate, but there is another axis which wraps on itself, because all the trajectories that we account for live on a circle. Okay, they go back to the same point after time beta. Okay. Okay. So this is the picture, and this is all for a single particle. Okay. Actually, I will.
Okay, thank you.
Yeah. All right. So now, what I want to do now is. Today, from now on, I'm no longer interested in the time-dependent problem, because for many body systems, it's extremely complicated and subtle. I'm going to be interested in statistical physics, okay, in getting thermodynamic quantities, equilibrium. But I want to extend it from a single particle where I only had one coordinate Q to a many-body problem, and I want to start with the simplest many-body problem that we already met in the beginning of this course. So remember how we started this course. We started by deriving Lagrangian and Hamiltonian for the problem of vibrations in one-dimensional string. Okay, and we use this simple example to show you, first of all, that you can write a theory that accounts for a case where there are infinitely many degrees of freedom, because there was a displacement field, what we called back then, we called it phi. Now let us call it Q, but it doesn't matter. But this displacement is defined for every point in space. So there is a one-dimensional axis, x. Okay, so this is let me write here. The 1D elastic string. So I remind you what was the problem there. We had a string stretched along the x-axis, and x here is not a dynamical variable. It's just a position. Okay, it's the continuum limit of an index of a chain of masses. Okay, just reminding from the first class, and then this is the equilibrium configuration of the string, and we then have some displacement. Okay, this displacement, which is we denote by Q. Okay. Here it is plotted as a function of Q. So for each x, I have some displacement Q of x. But Q was also a function of time. Okay? It was also a function of time, and that problem described a field. In fact, what we got is we wrote a Lagrangian for this, where the Lagrangian was defined as a functional of q of x and t. So it depended on q, on a function of two variables, x and t. And in fact, we could also extend it to higher dimensions and to replace the x by some r vector in a general dimension. Okay, so that was the problem. And now, let me remind you how the Lagrangian density of that problem looked like. This is just a reminder of something you already saw. We could write a Lagrangian that looked like half m q dot square minus a v of q, but the v of q was not a local function of q because it's a string, right? It's dependent on not on q itself, but on its derivative with respect to x. So the potential energy was something that we could write as half times some stiffness times the x gradient of q. Okay, it's something like that. Okay, this was the theory. Okay. Okay, very good. So now, so this is already a many-body problem because I no longer have one degree of freedom. I have many degrees, in fact, infinitely many degrees of freedom because the coordinate x is a continuous axis. Okay? But everything I did for a single particle, I can now, when I derive the path integral, I can now repeat for this. I just have to remember that q does not only single q, but there is q is a function of time, but it's also a function of x. And when I write an action, I have to integrate over x as well as t. And when I write the differential, this integral, multi-dimensional integral over trajectories, it's actually a multi-dimensional integral of all q of tau and x. Okay, so when I write a partition function, which describes just the same thing as usual, it's the generating function of all the thermodynamic quantities for such a problem at temperature, at finite temperature, characterized by the inverse of beta. I already have a closed expression for this, and I'm now writing it down. So it's the functional integral of all q of tau and x, where the only constraint is that there are boundary conditions at okay, so for every x, the q has to satisfy periodic boundary condition in the imaginary time axis, e to the minus s of q, the tau q, and the xq, where actually in our case, there is no direct dependence on q, on just q, only on the derivative. In general, I could add here a term that is like, I don't know, q squared, okay? But, or q to the fourth or something like that. But this is generally the case. I can also add some local terms, but the action, let me write explicitly what is the action.
You write it a little bit to right because I can see.
You can't see it. Wow. Okay. Yeah. Okay. So let me write it. Actually, I don't need this. את זה אתה יכול לראות?
Okay. Under the integral, you can see.
Okay. So, okay. So this is just that. This is just periodic boundary conditions. Okay. And now I'm writing the expression for S, which is this good? Okay. Everybody can see? All right. So this is what it is. It's an integral over tau going from 0 to beta and integral of over x going from, if it's finite, if it has a finite length, so suppose I have a chain with a finite length, then x goes from 0 to L, but I can also take it from minus infinity to infinity if it's infinite. But in any case, I have an integral over x and integral over tau of an expression that is now is going to be the Euclidean action. So it's not kinetic plus, it's not kinetic minus potential, but it's kinetic plus potential energy. And this is how it looks like, half rho s dx q. Okay? These are just brackets. Don't confuse it with write it just as regular brackets. Okay? This is the theory. Okay? And by the way, you can easily see that it's actually very easy to solve this integral. Why? First of all, let us think how would you solve it? How would you, if suppose I want to calculate this thing. Yes, exactly. So it's better to switch from Q of x and tau to the Fourier transform in both space and time, and then all the derivatives will just become omega square, omega and q, not q of k, sorry, omega and k, and then you just get Gaussian integral. It's very easy to solve. Okay, just technically, and I remind that what is actually this d of q is actually the limit where n goes to infinity of a product of dq of a product is over all x and tau of tau and x, dq of tau and x, and actually, so if I'm switching to Fourier space, instead of q of tau and x, I have q of k and omega, okay? And then the product goes over all omegas and all k's, okay? So formally, this is the differential. Maybe there's some normalization factor. You have to multiply it, but I don't care about it. Okay? Okay, good. So this is an example of how to easily extend to many-body problem, but it's a very specific and very simple many-body problem. There is something interesting I want to point out about this expression. If you look at the action, just the formal expression, what can you say about the relation between space and time? It's very symmetric, right? So if I'm forgetting that tau is describing imaginary time, which is a fancy mathematical concept we introduced just in order to map dynamics to thermodynamics. But formally it appears like another coordinate, right? So this expression looks like a two-dimensional integral over some functional, and notice that the time and space derivative, the time and space dependence are the same form. In fact, I can go from one to another by changing variables which will involve a velocity, right? I can define variables such that time times a velocity, and the velocity here is going to be the square root of rho s over m, is going to have the same dimensions as x, right? So, so formally, this looks like a two-dimensional problem, okay, of a classical thermodynamics. If you look at what you learned in your stat math course, is you wrote something that is called a free energy, right? And you calculated the partition functions as integral over e to the minus beta f. So that's exactly what you get here. If temperature is very high, what can you say about beta? If beta then is going to be very small. If beta is very small, the integral over tau effectively can be replaced by a factor of beta. Why? Because if tau is if the range of integration is very small, this term, which depends on tau, doesn't have a chance to change much. You can in fact neglect it, okay? And then it becomes just beta times integral over space, okay? And then you are back to what you are familiar with from stat math. But if beta is not small, and beta not small, and particularly if you're interested in zero temperature, what is zero temperature? Beta goes to infinity. Then here you can have an extended axis that goes to infinity, and this time derivative term will be important, but it looks formally as if we have a statistical physics problem in dimension 2 instead of dimension 1. Okay? So there is a mapping actually between quantum problem in D dimension to a classical statistical physics problem in D plus 1. Where the plus 1 is the time, okay? So this is just formal thing. Okay, good. So this example, we easily could write the answer, yes?
Rho s is a tension.
What?
Rho s, it's a tension.
Yeah, it's the what we call the stiffness. This is the same parameters we introduced a long time ago in the first class in this course. Okay? Okay, but it's a parameter. Okay, so, but many body problems cannot be described in terms of coordinate and momentum, right? I mean, we started from this to get something more general, which is we noticed that even this problem, if we want to quantize it, I mean, this was good for the classical field theory, but in order to quantize it, we have to switch to a Hamiltonian, and then we got this pi and phi, or pi and q, And we noticed that in order to represent the Hamiltonian in a nice way, we had once again to introduce the transformation to creation and annihilation operators. And this creation and annihilation later became our building block for any many-body problem which involves particles, many particles. Okay? And in this case, they also described bosonic particles, but we saw that it can be also extended to fermions. So what I want to do now is to switch from a problem where you express everything in terms of real variables, which are, or real operators, which are coordinate and momenta. I want to replace them by the building blocks of our many-body problem, which are the A and A daggers. Okay? Okay, so we already saw how to write states in this language, which are the Fock states. We wrote Hamiltonians, a single body, two body, etc. in terms of this. We also learned how to compute expectation values. We can do a lot with this. We can even do mean field approximation, how to evoke all that nice thing. But now I want to use these building blocks to derive a path integral formalism. Now, why do I want to do it? Because we saw already in the single particle problem that the path integral offers a much broader view on the problem, okay? In particular, it not only gives you the equation of motion, which is the classical trajectory, it gives you contributions from all possible quantum states, and it allows you to, if you want to compute the classical trajectory as some approximation, it allows you a method how to methodically calculate the corrections, the fluctuations. In a general many-body problem, we already saw that there is a mean field approximation, which is an approximation. Okay, and in fact, it's analogous to a classical trajectory in the sense that it's something that minimizes the energy and gives you an estimate of the ground state. But there are corrections, there are fluctuations, and I want to know how good is my approximation, whether it's justified, or also compute the corrections, which may have physical importance. So the path integral allows me to do it in a way that is very convenient for calculations. So in order to be able to do it, I want to repeat the derivation of the path integral we did last week, but not with coordinate and momentum, but rather with new set of states which are going to be eigenstates of these operators. Okay, so remember, what was the trick that we used in order to derive the path integral? The trick was, because we noticed that we had a Hamiltonian that is a function of P and Q, we first divided the time axis to small slots, right? And we looked at time steps, very tiny time steps. And in each time step, we inserted a resolution of identity in terms of eigenstates of Q and P. And inserting these eigenstates allowed us to replace operators by their eigenvalues. And that's what eventually led us to something that is just an integral over numbers and not operators. Here I want to do the same, but my Hamiltonian is no longer a function of P of Q. The Hamiltonian is some functional of A's and A daggers. Okay? Here, by the way, alpha is some quantum number of the single particle states that allows us to define all the annihilation and creation operators. Okay? It's some basis. So this is, the Hamiltonian is naturally expressed in terms of A and A dagger. And I want to have something that will allow me to write a resolution of identity in terms of states that are for which are eigenstates of these. Okay, what are these? So I have to define a set of states that are so-called coherent states. I don't know if some of you may have seen them, especially in optics, okay? And now I emphasize that all I'm doing today is for bosons, okay? So A and A dagger are bosonic operators. They obey the commutators. Okay, these are, okay? And of course, more generally, the alpha and alpha prime give me a delta of alpha and alpha prime, but it's a commutator, not anti-commutator. And for bosons, everything I'm doing today is good. If we want to extend it for fermions, there is a problem. And I'm not sure, unfortunately, that we'll get to it this year. Okay? So we'll see. Let's first start with this. So what are coherent states? The definition is, I define a state, first of all, I'm denoting them by phi, where phi is a vector of phi alphas, where alphas are these quantum numbers, okay? And these phi's are some complex numbers. And the state phi is defined in such a way that when I apply any annihilation operator, A alpha, on phi, I get an eigenvalue times phi. So in other words, the coherent states are eigenvectors of the annihilation operator. And their eigenvalues are phi alpha. Okay? Okay, and this is true for every alpha. So the phi is actually a vector and the numbers phi alpha are complex. Okay? Now, first of all, if I'm writing this, by definition, I can write the conjugate, the Hermitian conjugate equation. So if I do Hermitian conjugate on both sides, I get that if I apply A alpha dagger acting on the left, it gives me phi alpha bar. Okay? And we are going to denote a complex conjugate by bar. Okay? So this is just for setting up the notations the way they appear in the books. What we usually call phi star is phi bar. Okay? Okay, so this is a definition. This is a definition, but now we would like to be able to express phi in terms of Fock states, but because we already learned how to present all wave functions in the language of second quantization, and we saw that the basis of states that we were accustomed to work with are something of the form a product over alpha of some normalization factor A alpha dagger to the power n alpha acting on the vacuum. Okay, this was the Fock state. Okay, and Fock state has a well-defined number of particles. Now, the coherent state has to obey that it's an eigenstate of an annihilation operator. So first of all, it clearly cannot be a Fock state, right? In fact, we know that what is A alpha doing on any Fock state? It reduces the number of particles, right? So it cannot be an eigenvalue. It cannot be an eigenvector, right? The Fock state cannot be an eigenvalue because by definition, A alpha acting on F always gives you one less particle. Okay? So phi is, it must be a superposition of many Fock states with different particle numbers. And I'm claiming that I have a closed expression for it. You're going to prove it in your homework. It's not a complicated proof. It has the following form. It's an exponential of a sum over alpha, phi alpha, A alpha dagger acting on the vacuum. Okay? So, and it is actually straightforward to prove that this does the job. Okay, if you act on it with A alpha, you get phi alpha times the same. Okay, good. So that's something you are going to prove. And when I'm writing, what do I mean by an exponential of a sum of operators? Yeah, it's just I have to make a meaning for it. I have to write the exponential as a Taylor expansion. Okay, you've already seen it. This is true for any operator that I put in the exponent, and you see that when I open this to a Taylor expansion, I basically have a sum of infinitely many terms with different particle numbers, right? Because it will have these two higher and higher powers. Okay? Great. So this is a coherent state. Now there is another identity you can prove directly. Yeah? There's another identity.
Thank you.
Okay? There's another identity that I can prove. So, if I take this phi and I apply a dagger alpha on phi, what do I get? Okay, maybe it's not so easy to see from here, but when I write the result, you'll immediately recognize why it is true. If you take this phi and you take the derivative with respect to phi alpha, you're going to get A alpha dagger times phi, right? You see why? Take the derivative with respect to phi. Phi is just a number, so you can take the derivative. It gives you the exponent times whatever multiplies phi alpha, which is A alpha delta. Okay? So if I'm looking at, let us look at this, these two identities. Phi is, if I want to, phi is an eigenvector of A, of the annihilation, with eigenvalue phi, okay? If I want to represent A dagger, the operator A dagger in the basis where, which diagonalizes A, it gives me a derivative with respect to phi. What does it remind us of? Okay, this relation. There are two operators, A and A dagger. The eigenstates of one, or the eigenvalue, the eigenstates of one. If I want to represent the other in the same basis, it becomes a derivative. What does it remind us of? Remez? Q and, so if I'm looking at the operator Q, the coordinate for just the particle, and I want to represent the momentum in position space, how does the momentum look like? It's minus IH bar dx, right? So it's a derivative. Right, so just a reminder, Q in real space representation is Q, and P is minus I dq. Okay, we're working at H bar equal 1, so okay. So here we get the same thing, right? So in a sense, the relation between A dagger and A is like momentum and coordinate, except where there's one important difference. There's no minus I. Okay, the derivative is just real derivative. It's just a derivative. Okay, and why am I saying it? Because it already allows us to guess how will if I'm looking at the overlap between two coherent states, or the inner product between some phi and some other phi state, it very much looks like the real space representation of wave functions of a free particle. So let me remind you the analogy. So if I want to express the wave function psi of pi, this is for a single particle. Sorry, let me call it Q. Okay, this is the wave function of a particle with momentum P as a function, written as a function of Q. How does it look like? It has some normalization factor times e to the I P dot Q. Okay, actually this is true for general dimension, right? This is the wave function of a free particle. But what is this thing? If I write it in a Bra and Kent notation, it's the overlap between the state P and the state Q. With well-defined momentum and well-defined Q. Okay? Now, in analogy with that, I see that this one is is an eigenstate of the momentum. This is the eigenstate of coordinate of, sorry, in analogy with this, if I look at the overlap between some phi and some phi prime, okay, well, the phi and phi primes are, this is a wave vector, sorry, it's a vector of phi alphas, and this is a row vector of phi bar, because it's on the left. So this looks like how to write a coherent state wave function when I project it on an eigenstate of phi prime, and I'm guessing that just in analogy with this, it will have the form where this product is actually, it's like a scalar product. Let me write it more explicitly. Yeah. Okay, this is what it means. Okay. Actually, if we write this prime, okay, it's phi prime alpha bar. Okay. Okay, so actually, so I try to make it in analogy with this momentum and coordinate, but actually, you can just calculate it explicitly. Okay, and you'll also get a homework exercise. Just take the definition and compute this matrix element. Okay? And you see how it looks. So actually, if you want, I write it explicitly. How does this look like? It's the vacuum here, e to the sum over alpha, phi alpha bar, a alpha, right? Okay, so when you calculate the overlap between this and this with a prime, which is different parameters here, you'll see that it's just calculating some vacuum expectation value. Okay? Good. Now there is one problem with this. So we would like to now switch in all our description of wave function to a basis of coherent states. These are the natural things that will help us do a path integral, because they are eigenvectors of the annihilation operator. But there is one little problem, and that is if I'm now taking a special case of this, okay? Taking a special case, this is for some phi and some phi prime, two different vectors, but I can take the special case that phi equals phi prime. What do I get then? It's the inner product of phi and phi with the same phi, and if I just plug in the expression, it's sum over phi alpha bar phi alpha, but phi alpha bar phi alpha, that is the same phi, is nothing but phi alpha absolute value squared. Okay, it's a complex number the sum of square of complex number in absolute value. Okay? Okay, what can I say about this expression? Notice that it's exponential of something positive, right? It may even be very large and positive, but it's positive. Therefore, it's bigger than 1, right? But what is it? This is supposed to be the overlap of a coherent state with itself, which usually, if in a normal kind of basis, we would like it to be 1, right? We like to normalize it to 1. And we see that it actually gives me something that is bigger than 1. Okay? Now, that suggests that actually the coherent states are, as opposed to the Fock states do obey that you can always normalize them such that they give you, especially the way I wrote it before, the Fock states are normalized and their overlap is always 1. Okay, their norm is always 1. The coherent states have a norm that is bigger than 1. That means that it's not a complete set, it's a so-called over-complete set. Okay, it doesn't give me a unique representation of any state. So in that sense, it's not a useful basis for computing an expansion of any wave function. But for our sake, for the purpose that we want to use it, it doesn't matter. Why? Because we can always say, okay, this is whatever it is. We know what it is. We know it's bigger than 1, fine. But then if I want to write a resolution of identity in terms of coherent states, I better divide by this factor to get rid of the factor of bigger than 1. Okay? Or in other words, I can define now a resolution of identity in terms of coherent state. So let me remind you what in general we do is if we have a complete set, just a regular orthonormal basis, which is a complete set, we can always write the resolution of identity like this, right? Here, I can once again write it as a sum, or actually an integral over all projectors, but the projectors have to be divided by the non-trivial norm. So this is how we define it. Let me write it. Here we have a differential. We integrate over all the possible phi's of let me write it here. And here we put 1 over the overlap times phi. Okay? And because we divided, that will it will normalize it back to 1. So more explicitly, how shall I find it? Let me first define what is the differential, okay? It's the product over all alpha of d phi alpha bar, d phi alpha divided by pi. Why do I divide by pi? This is because there is a normalization factor for Gaussian integrals in the complex plane. I will show it later, but let's just accept it. It's more convenient to introduce a factor pi here. And for each alpha, I integrate over the phi alpha and phi alpha bar. Okay? Okay? Did you ever see integrals in the complex plane? Z bar? I don't think you have. Okay. All right, but let's just keep it for that. Actually, okay, maybe I better write it down. Because if you haven't seen it before, I'm going to use it. The integral, let me define here an integral. Shall I find it? Yeah. So W here is some parameter, okay, and I have an integral of this form where Z is x plus iy, and Z bar is x minus iy, and dz bar is equivalent to integral dx dy. We integrate over the real and imaginary of this. Okay? So this thing is what I called d of z bar. Okay, now what is the result of this integral? If you convert it to x and y, you see that it actually gives you just a double Gaussian integral. And in the Gaussian integral, the result is square root of pi over the parameter w, but because it's double, the square root goes away and you're going to get just 1 over w. Okay, so this is why I included the pi here. The pi I moved into the differential. So defined in this way, if w equals 1, I just get 1. Okay? So this formula is very important. Okay? Yeah, so it is what the way you want to interpret it is just the integral over the real part is real part of phi, the integral of the imaginary of phi, okay, for each phi. Okay, but forgetting about it, just call it differential and use this formula for any Gaussian integral of complex numbers.
זה עובד בשביל שום הכפלה של חלק ממשי כפול מדומה בשני משתתו, חלק ממשי בתוך.
Yeah, exactly. Right. Okay? Okay, great. So once again, in the resolution of identity, I do an integral over all phi and I define the differential in such a way. And then I have phi, the projector, but I have to divide by the norm because the norm is not 1. So let me write the final result because we know what is the norm. It's just this, right? So let me write it here. What? No, this I'm not erasing it. I will just write the final result. from the resolution of identity. So, sorry, it will be just phi bar phi e to the, now because it's 1 over the norm, it's e to the minus sum over alpha, phi alpha bar phi alpha, or phi alpha absolute value square, doesn't matter, times phi. Okay. Okay. So now we have a resolution of identity in terms of coherent states. And now I'm going back to the thing that I want to calculate and see how we use it. Okay. So, so let me remind you of the trick. This I can erase, right? It's okay? What do we want to calculate? We want to calculate a partition function which is sum over n e to the minus beta h, and in fact, let me even be more general. I want to put here the grand canonical Hamiltonian, okay? So this is in the grand canonical ensemble, the partition function is a function of beta, which is the inverse temperature, and the chemical potential. Okay, so you don't have a fixed particle number. We don't want to work in fixed particle number because we have a many-body problem. We can create and annihilate particles. So it's more convenient to work in a grand canonical ensemble, and then the Hamiltonian is replaced by h minus mu n, where n is the number operator. Okay? This is what we want to calculate. And here, the Hamiltonian and the number operator, everything is written in terms of A alpha and A alpha beta. Okay? Okay, so now what do we want? We want to look at this, this thing, we want to look at it as a path integral. Namely, we want to divide the imaginary time beta into small pieces and write the exponent as e to the minus h times d tau, small bits, and in between them we'll insert many times the resolution of identity. That's the idea. The same thing we did for a single particle. But before I do it, I notice that as I define the partition function, here n is not a coherent state. It's some basis of some complete state of for example, Fock states, okay? It's some complete basis, a regular one. So I first of all want to switch to coherent state, and the way I do it is, or I can do it, is I can stick here the resolution of identity. Okay, I can stick here a resolution of identity, written in terms of some coherent state phi, or let me call it psi for that matter, it doesn't matter. And I'm now writing it explicitly. So this is integral d psi e to the minus psi squared, which is a short for what I've written here, psi. Okay, this is what I'm sticking here before I write the exponent. Okay? Okay, so let's see what we get from it. So now I have sum over n, and notice that here I have an overlap between a state n and a state psi, right? But everything up front is a number that I can take out to the beginning. I can move, because it's just a number, the order doesn't matter, I can push the integral sign and the normalization factor. All of this I can push to the left. And then inside the integral, what I have is n psi e to the minus beta h minus mu n, sandwiched with psi, with n. Right? You see what I've done? Okay, I just plugged in this, and I took the factor of the integral and all this number, I moved it to the beginning. That's all. But now you see what I got here. Now I got something that inside the integral and the sum, I have both a sum and an integral. Inside what I have is a number times a number, right? Because this is a matrix element, and this is just some complex number, right? Since it's a number, I'm happily moving it. I can move it anywhere. In particular, I can move it here, right? But notice what will happen if I move it here. Okay, now let's erase this and write down. Then I'm getting that the partition function is given by sum over n integral over psi bar of psi e to the minus beta h minus mu n times n psi. Right? Okay. But now I can, I have a great simplification. I can get rid of the sum over n. You see, I didn't even tell you what are the n's. I just told you some complete basis. Why can I get rid of it? Because if I just sum over n, what I get in the summation is a resolution of identity, right? So it essentially disappears, and I'm getting an expression for z, which is just the integral over psi, and you see then what I get inside the integral is nothing but, and I forgot, sorry, I forgot the factor of e to the minus psi square. Okay. So let me write it here. So it's e to the minus psi square times the matrix element the diagonal matrix element of e to the minus beta of this time, not the imaginary time evolution operator, in the state psi. Okay? And this object, I can actually calculate using a path integral, just using the same idea, except that now the states, so you see it's similar to what we got before with the Q, but instead of the states Q, which is coordinate of some real coordinate here, the psi's are complex vectors and they are coherent states. They are coherent states and there is this factor, okay? Which is not, in fact, it's going to give us something very similar to what we got before with the path integral of a single particle. But we essentially have a good prescription of how to compute it. So what will be the idea? To get the path integral, the idea is I want to get rid of the commutators by dividing my time to small pieces, in each of which the operators are nearly commuting. That's the idea. So it's exactly the same trick. I take the operator that I have here in the exponent, e to the minus beta h minus mu n. Or actually, let me just call it for short, h grand canonical, okay? And I see that I can write it as a product of e to the minus h grand canonical d tau times e to the minus h grand canonical d tau times dot dot dot, and I do it n times, where n is beta divided by d tau. Okay? Okay, d tau is the size of the small time step, which I'm going eventually to send to zero, to the limit d tau is infinitesimal. And then I actually replace what I did here is exactly just as I had before for the single particle, because I can neglect the commutators of operators when d tau is sufficiently small, I can replace a sum by a product. Okay? And now what will I do? I will now put a resolution of identity. I'll do it n times, okay? And each time I write the resolution of identity in terms of some other field that I give it an index j. Let's call it j, not n, not to confuse. So if I'm looking at some intermediate step somewhere in the middle, the resolution of identity is going to be d psi j e to the minus psi j square psi j, where j is a parameterization of the time step. So let me describe it. So if this is my time axis, it's going from 0 to beta, okay, and this is the tau axis. It's tau going from 0 to beta, and I divide it to to small time steps of size d tau, then the jth step, I call the index j, and j is between 1 and n. Okay? Okay? Okay, so that's the idea. That's the idea. And therefore, if I'm looking at the jth step, what I'm going to get is, because I'm putting a resolution of identity at the two sides of each of these operators, I replace it by a matrix element between some psi j and psi j plus 1. Okay? So let me write it down. What I get after in the jth term in the string in the product, I will get something like this, integral d psi j. Okay, all the integrals I'm turning to the left anyway, but it's there. Okay, and then I get e to the minus psi j square times, sorry, psi j plus 1, because this is on the left, and psi j plus 1 e to the minus beta h grand canonical and psi j. Okay, well, I have to remember that each of the psi j's, it's itself a vector, because, so for example, psi j square is actually a sum over alpha of psi j alpha square. Okay, so the psi j is itself a vector, okay, which has many values. But here alpha, the j is a parameterization of the time axis, and alpha is some quantum number, which defines my annihilation and creation operators in the Hamiltonian language. Okay? So this is it, and I ran out of time, so next week we're going to see that we actually have a very simple closed expression for this. And just like what we did for the single particle, eventually, after getting this infinite product of many such matrix elements, I'm going to get something that in the continuum limit, where I take j to a continuum time variable tau, it will give me a path integral. And in the path integral, I will get something that everything is just numbers, and these are the values of psi, of tau, and alpha. Okay? So we'll see it next week. Yeah. Okay? Questions? It's a bit technical, but eventually it will give us something very pretty. Okay. Very good. So the next hour is going to be given by Sar. So I'll see you next week.
למדנו על זה לפני. ה-BCS לא...
היה לנו תרגול על זה?
לא עשית לנו תרגול?
היה שבועיים שלא ראיתי פה.
לא פשוט היא אמרה BCS, ואני כזה... מה זה BCS? עכשיו נדע מה זה.
היא לא דיברה איתך על BCS?
לא, היא דיברה איתם. אמרה שיש את זה בטוטוריאל.
זמן חיכה טוב 2 דקות האלה, בקשר של אנשים. Should we wait 2 minutes? Guess that will be. Super enough. Okay. Today we'll explore a little bit the following Hamiltonian. איפה מפריע לך? Where's the problem?
It's okay. בסדר.
Stop laughing. Okay. This is a Hamiltonian that you saw in class for the BCS, where we start from the BCS theory. Our point is to take this Hamiltonian, analyze it a little bit, and show that there is a superconductivity in here. In reality, I'm just going to spoil it for you. We're not going to prove superconductivity. It's a bit above our paycheck, but I will add like extra material in the website. But we'll do half the way there. Okay. So why don't we just use this Hamiltonian as it is? Did I write A here?
Yes.
C, because we're using fermions. So, if I want to simplify this Hamiltonian, it's also, god damn it. That's what happened when I tried to do it by hand. Alright.
Minus V?
Minus V.
Okay.
Well, V is greater than 0. Okay? First of all, before we even start, before I talk about it, I just want to say our motivation. Our motivation is mostly this part. This is a fourth order operator within Hamiltonian, something that it's a bit that it's more complicated than the operators pair that we know and love. So I want to take this term, but mostly want to take this term and simplify it. Where in the end, we're also going to find the eigenstates and eigenvalues of this Hamiltonian. Now let's see what actually happens here? We have the standard free electron energy, and then we have here some interaction term. This interaction term takes two electrons that approaches each other and transforms some kinetic some wavelength between them. Right? We actually see here, because V is positive, having two electrons approaching each other, because K tag minus K tag, they're the same K vector but in different direction. It actually reduces our energy. So it's beneficial to have pairs coming toward each other. And we'll go back to the pairs in a bit. Okay. Last thing that we can talk about is that the vacuum state, what was the ground state for the free electron Hamiltonian, doesn't work here, because we have this absolutely positive term which has a minus before it, so it's overall it's an absolutely negative term. So we can assume that the ground state is it's not actually a vacuum state, it's something a little bit different than the vacuum state. We'll have some addition to it. Alright, so this is our motivation. And now, to try to simplify this equation, I want to look at this for a second, this interaction part, and notice that for every up spin you have a positive k, and every down spin you have a negative k. Of course, because it's the sum of a k vector, it's sum from minus infinity to infinity, but they will have a minus between them. So we can simplify the k up and the k vector up and minus k vector down is simply saying k vector up equals k, and the index k vector down be minus k. Simplify our writing. And now I want to do the same thing here. Okay, so I'm just going to take this free electron Hamiltonian. Second, vector sigma. I'm going to open up the sigma sum here, the spin sum, and then have ck up plus ck vector down, tרגול down. Okay.
למה אתה שם את הפסיק פה ל-K, הסכום החיצוני?
באתי לכתוב גם את הסיגמה, אבל בסוף פתחתי לפי הספין. Okay, so all we have to do is basically put a minus in this k vector, because this sum is from minus infinity to infinity. We can just, for this term, flip the sum over. So I can just add minuses here. And the last thing that I want to do, which will be clearer later, is I want to flip those two. Right here, so because we know that C dagger C equal to 1, in order to flip them, if I flip them, it will go sum over K, K, CK dagger CK plus C minus K, C minus K dagger plus some sum over the ones. Actually, here there's a minus. Everything is going up to a sign. It's fine. Okay. In the tutorial notebook, we keep track of this constant, but I'm just gonna ignore it because again energy is up to constant, so I'm just gonna remove it. So overall, our Hamiltonian equal to sum over k. So k dagger k plus minus k minus k plus tag k dagger minus k tag k
אותך מינוס בחיבה הראשונה של הפרצה.
איך כל פעם אני מפספס אותו? So, let's assume, one second, that we have a ground state. We will call it a ground state, I will say a GS, and I'll call it.
סחי, למה זה פה למטה שני סכומים ולא סכום אחד?
Notice that the flipping of this term gives us plus 1, and then the plus 1 will be multiplied by constant. So I take the entire constant outside, and then I decide to ignore it.
פשוט רשמת את כל האופציות האפשריות של הדבר הזה פשוט? פשוט במקום לצייר סימה, אז פשוט רשמת את זה פעמיים?
I don't understand.
רגע, למה אנחנו פה שני סכומים ולא השלמה?
These two sums are like two separate sums, they're not a sum within a sum.
לא, אבל זה נבע אולי כי יש את המקרה שבו הספינים הם הפוכים.
No, this sum came from here. Here is C dagger C plus C dagger. I take C dagger C to the other side and we get 1 minus C dagger C. So the 1, there's supposed to be plus 1 here. So instead of putting plus 1 here, I just took it out. It's a constant, so I can move it. Okay, so I assume that we have some sort of ground state. I'll call it BCS. Now I'll make another assumption. This one is not very trivial. That make an assumption that BCS, the state BCS, has some expectation value over C dagger K, C minus K dagger. Right? Basically, yeah, this is just assumption of reliable oscillator, but if you want it like, you know what, we will understand this assumption a bit better in a moment, at the end. So, now I want to break this down to a form that we're more used to. Again, just two second order operators instead of fourth order operators. For that, I like to show you what we call mean field approximation. Okay. Mean field approximation states that if we have two operators, we can say that the multiplication of A and B equal to A as B plus A times the expectation value of B plus the expectation value of A and the expectation value of B. With the condition if A psi B slow very I'm not sure it's what. If A, okay, I'm just gonna say it because I'm not sure how to write. If A and B change, if I assume that A and B only change slightly, they have some mean value, and they have some change around it. Basically, if I can write A, for example, if A, I can write A as A plus delta A. I mean, you have some expectation value and some perturbation around it. Okay, so let's prove this equation real quick. So A equals this, B also equals expectation value of B plus delta B.
When you write delta, it means what it means.
That means that there's a small change, like almost like you can take a function and make a series out of it, a Taylor series. You can do something. Don't kill me, cameras. You can do something very similar with operators, like expand it in orders of changes in the operators. So this will be like, I say there's a zero order value to the operator, which is the mean, and some first order small change, a small fluctuation that we get from it, right? So I multiply them both. I have the average times average, AB, right, plus A delta B plus delta A plus. Right. Because I assume there's a small change, you can ignore this part because it's the second order of a small thing. And let's take this multiplication of the averages and add it to this term for you. Yep.
So delta it's like sorry for the question, but delta it's like the bigger delta. It's the
small
difference between two. It's like difference between two headache.
You should have talked in class about perturbation theory.
Okay.
Talked about it. So this is exactly it. That's the delta here. It means that the operator or the expectation value of the operator changes by a small operator, a very, very small operator. Okay, so let's combine these two together. Second, we'll get the average of A times the average of B plus delta B. This is just B, the operator B here. Of course, you can write it in your notebooks. It will be it will be more organized in the class note, which you can also write in your notebook. Again, and so we'll do the same here in this one. We'll add and subtract another multiplication of the mean value, and get here the A operator minus the extra mean field value, multiplication. Every time. Yeah, I wrote a plus. It's a minus here. I'm sorry. Okay. Okay.
No.
Oh.
No. Yeah.
I'm going to erase the top one. Now, remember I made some arbitrary assumption here that the ground state of the system has some expectation value for these two pairs of operators, which we can see it over here. And of course, if they have some expectation value for the dagger of those operators, so the complex conjugate of this expectation value will just be the expectation value of these two annihilation operators. Okay, so I can put here in this theorem A equals C dagger K, C dagger minus K, and B equals C minus K tag C K tag. Right. So I can write it as plus an extra constant term that I won't even write because I hate constants, so I kick them out. Okay. This will just be the multiplication of these two expectation values. But again, constant. I don't care.
It's in tutorial, right?
All of this is in the tutorial. I'm just trying to abbreviate it a little bit so it will fit.
Minus, yeah.
How does it happen? How? This point is supernatural. All right. Anyway, this constant is 0. I don't care about it. It's 0. Okay. So let me say this. We have here a multiplication of two sums. Okay. Or we can even write this term as a sum over k. What's it doing? Yeah. For each one of these k tag, we have this term ck dagger c minus k dagger this b time ck c minus k ck. All right. So I'll take this entire term and call it this times v. I'll call this delta, big delta.
אם בשורה הראשונה פה הנחנו שיש...
שורה ראשונה איפה?
ב-mean field approximation, הנחת שיש לך מינוס. למה בשורה השלישית שנה מינוס? גם כן, לצורך העקבות.
איפה? פה?
לא, אני בשורה הראשונה של AB, הגעת למינוס ערך תצפית של A כפול ערך תצפית של B. למה בשורה 3 לא קיבלנו גם כן שם מינוס?
פה?
Yeah.
כן.
Here, notice that we took one A times B to the second term to get this. Oh. And then I took another one and added and put it here. So I add to add AB minus AB.
צריך להפוך את ה-A ל-A פחות ממוצע של A, ואז לפתוח סוגריים, ואז יהיה 5.
ועוד, פעם אתה טעית. ועוד הממוצע שלי.
לא, דלתה A שווה ל-A פחות ממוצע של A.
כן, כן.
לא, זה ברור לי, אבל... בגלל שהחצבת את לפני דלתה, זה מה שאתה בעצם.
Yeah, I want to take this to be delta A plus A times B. So to do this, I have to add and subtract A times B.
Okay.
The mean field, the expectation value. Blah, blah, blah. Okay, so we define this delta here, and we can rewrite again this equation. Now, here, because we have this delta and this here is a delta, so we have two different sums, unrelated sums. I can change this this index from k tag to k, all right? This index from k tag to k, and put those two in the same sum over k. And I can take them all here and put this here. So overall, this. And all the time. It needs to be delta, so it will be consistent. Plus. All of this is in one big sum. All of them. Now, let me define a vector. I'll just define to you this. It's like K vector, which equals to CK C minus K dot. Okay. Then complex conjugate. I have great faith in you, so I'm just going to write, if I'll try to use these two vectors and make this into a multiplication of two vectors in a matrix, I have faith in you that you agree with me. That this Hamiltonian can be rewritten as plus all the constants that I ignore. Right? You can check, you can do the multiplication yourself and see that this will be the answer. Which is precisely why I swapped them. Which is why I swapped them, so I can put it in a matrix. It's a personal secret. Alright. So we almost made it. We have a Hamiltonian that works fully on second order operators only. And we even have a very nice matrix here that if we diagonalize it somehow, we'll get the diagonalized Hamiltonian and the problem will basically be solved. So here I'm gonna show you a very reliable transformation. That if you're not sure, you have some sort of problem and you're not sure how to solve it, it's a good guess for many problems. It's called the Bogoliarov transformation. It's going to take me a second to write the name. Bogoliarov. Graph transformation looks as following. This is our new operator. Equals to UK. Okay. Dagger and dagger minus K equals CK star CK plus UK.
What this is X?
1 second.
X is dagger.
Where's the X?
Vx. It's dagger.
Complex conjugate.
Ah, כוכבית.
Yeah. Star. Good. Okay.
Small star.
Just before we actually test this transformation, I'm just gonna say one thing. The Bogoliubov transformation, you will find that in all the cases that the Bogoliubov transformation applies, you can take U and V to be real numbers. Just as a note, I'm not gonna prove it, I'm not gonna show it, I'm not gonna talk about it anymore. It can be, we can choose them to be real. So I'm just gonna ignore the star and the absolute value and all the rest. You need to okay. So
לאן קישרת את המכפלה של ה-V בסכום שמה שעשית? פה, במכפלה של ה-V בסכום,
This?
כן, לאן קישרת את זה לביטוי המקורי? פשוט חיסרת את זה?
Yeah, I want to remove. No need to constant.
פשוט חיסרת את זה שם, שחררת שם את המינוס.
No, I didn't.
לא, אפילו את הדבר הזה שרשמתי.
This minus came from here. The V here in the definition of delta.
אז זה היה חסר פה מינוס דלתה כפול מינוס.
No, I didn't put the minus here because I wanted to keep the minus.
רגע, אז למה הביטוי הזה קיים? איך אתה מחבר אותו לביטוי המקורי שאני מתעניין?
Which one? This?
כן, הביטוי הזה איך מחובר לו בסוף לביטוי שאני מתעניין?
This one?
כן.
It's here. So part of.
כאילו פשוט רשמת את הביטוי הראשון פה מהשניים. אוקיי.
Of course, there's another sum over K tag, but I can separate the sums. Oh. Alright, so if we'll write the Bogoliubov transformation using matrix and vectors, because we know how to play with them. We get that okay, where we have here our new operator vector, which we'll, for example, call the capital sigma. I always forget the name of this letter. Capital sigma. Let's see. Yes. Equals the transformation matrix.
What is sigma? That is gamma.
This is gamma. Oh my god, I'm so embarrassed. How can I be in the second year of doctoral and not remember
You don't remember
all the letters? How can I not
all
speak
the-
ancient Greek when I'm in like
But you need. It's for physics. You
I'm
need.
opening Duolingo on ancient Greek and I'll study. Thank you. Okay. So we have everything we need to fully prove and the chain transformation. We have the output vector, the input vector, and the transformation matrix. And we know that this transformation need to follow basically be self-consistent, right? Let's start with the relation between gamma k and gamma minus k. So we know that gamma k again. Writing really quick, UK CK minus VK C minus K dagger. Now I'm gonna take this gamma and take the complex conjugate of it and flip the K sign. So gamma minus K dagger equals to U minus K, C minus K, minus V minus K, C, C minus K. This one is CK. No, without dagger. Here is dagger. Right, just simple. Then I can take this result here and check to equate it to the second equation in the definition. Here we see that UK must be equal U minus K. Right? UK equal U minus K. In the same way, you can see that VK equals to minus V minus K. All right. So we know that for a start, we know that U has to be even function and V has to be an odd function. I'm going to write in the middle. Right. Second, we know that this matrix has to be unitary. So that that UK equals to UK squared plus VK squared must be equal to 1. So UK and VK will be a sinus and cosine function, but we already know that UK is even and VK is odd, so we can assign UK equals cos of some phase, and VK must be equal to sine of some K.
למה אין לך דטרמיננטה שזה צריכה להיות 1?
Because if I want to create a preserving transformation, it has to be a unitary transformation. The unitary transformation, it has two different conditions. One, it has to be have a determinant of 1. Why this word? Yeah, determinant of 1. And the second condition is that UK dagger equal to I. This is a linear transformation, normal linear transformation in the קוונטים.
כי אתה בעצם חייב שהדבר הזה יהיה אוניטרי,
כן.
מה שאתה דורש מהדבר הזה. מישהו יקיים את התנאי הזה כדי שיוכל שיש לו טרנספורמציה טיפולית ולא.
Okay. Yeah, but I'm not going to do this condition now. I'll do another one.
And why you erase it? Why you erase it?
Because I'm going to do a different condition. This is condition 1, condition 2. Condition 2 states in every unitary transformation that the commutation between gamma k and gamma k dagger equal to commutation relation, in this case anti-commutation relation. Let's see if this is okay. So gamma k dagger equals to okay ck Plus there's a plus between those two lines.
Why k tag if we put both k in the left?
Thank you for keeping me honest. Okay. Now, to open sum in the commutation relation, it just open to 4 different commutation relations, but I'm just going to write 2 because the commutation relation between 2 different indexes by definition 0. So you just have u k u minus k time. One equals u minus k is equal to uk, so uk times uk tag plus v minus k equals minus vk, so it's vk tag, and now those two under commutation relation will give us a delta k tag.
למה אתה חייב אבל ש-UK יש שווה ל-U מינוס K ו-VK יש שווה ל-מינוס V מינוס K? למה אתה חייב להיות?
I took this equation complex conjugate and put a minus on the k on the index and compared it. Just compared it to this. Okay?
Sir, while opening the anti-commutator relation, why didn't you take UV terms?
That's, for example, this one and this one. Because even without the need for dagger, those are 2 different indices.
Okay.
But you can also say that there's those are both annihilation operator. It's also okay. Okay. So because of this delta here, we can, the entire result here will be 0 unless both k's will be the same. If both k's are the same, we have uk squared plus vk squared, which you already know is 1. So go on, this is delta k time. Very good.
רגע, למה גם מיחס האנטי-קומוטציה השני יוצא דלטה?
Same reason.
לא, אבל כאילו, צריך לעשות להם מינוס.
Delta of minus k tag is just flip the sign.
כן, שזה אנטי-קומוטציה וזה דלטה.
Wow, we have a lot of time. Okay. Next, I want to find the inverse relation. I'm going to look at equation uk gamma k plus bk minus k. Again. From first one, uk squared k minus uk vk again from the second one, vk squared ck plus uk vk c minus k dot. These two cancel out. We get that uk squared plus vk squared equals to 1. So we see that ck equals uk gamma k plus vk gamma minus k. Again. Right? In the same way, we can also find c minus k dagger equal to minus vk k plus uk minus k dagger. We can see that our matrix, using the same convention with uk as the first line, will be where gamma k is the first line, will just be uk vk minus vk uk, which is okay. So with this, this is not this. So with this, we basically prove that u dagger equals I. Almost done. Almost done. Now just to do the transformation itself for the Hamiltonian. Right. If we'll call this, for example, hk, now you'll see that h is equal to sum over k, psi k, uk dagger k, hk, uk dagger k, k. All right. Those two, we already know what they're equal to. Okay, here.
Forgot the plus on the right.
This is dagger, right? I think this is dagger. Right? We only need to find the Hamiltonian. Hamiltonian, I'll call it. Call this Hamiltonian hk diagonalized. Should be equal to something of the form hk 0, 0. Try to find this. That's my guess. The middle house. This is going to be a little bit long, multiplying all the matrices. So I'm just going to save you the trouble and do the arithmetics myself. And just show you the way. Screen D equal to. Notice that I changed to the cosine and sine notation. Yeah. Another point I didn't mention that you can take those delta. We can also assume these deltas to be real. Can I? Just need some more space. We're supposed to finish at 7.5, right? So we might take a very short break soon. You can check me on this if you want. It's just very long. Alright. You can see those two are the same. Those two are opposite, negative of one another. And we can also say from before, how I expect this matrix to be EK equal to epsilon k cosinus 2 delta k plus delta sinus 2 delta k, and 0 equal to minus delta cosine 2 delta k plus epsilon k sine
So it's fun.
I'm just going to give just going to finish this equation, then we're going to take a break because because my tablet is tired, very tired. I was working with it all day and I forgot to check. Yeah, it's very unprofessional. I'm just gonna do it by hand because again, writing it will take a while. If we square this equation and square this equation and sum them together, you'll see that the cross term will cancel out, obviously, and then you will have a delta squared times cos squared plus sine squared, and a epsilon k squared cos squared plus sine squared, so it's going to be 1. We get ek squared equals 2 cos squared plus k squared. I just want to remind you that this epsilon k is the energy of the ground state. So even before we continue and finish this all, we see that our energies will be the ground state plus some gap energy. Okay? And then putting this back into the first equation and doing some more arithmetics, we'll get that. Okay. Don't worry, you have something that's very similar to this in your homework to do explicitly. So don't worry. No pressure.
Thanks.
You're welcome. Okay, equal to sine. Okay. Let's take a, okay, let's do it like that. We'll take, what's the time? Let's take a 10-minute break, and then we'll talk about this result and go back to our BCS ground state and look at it. That's basically all we left. We had a really good time, so we have some time for a break.
How?
10 minutes till 7:05.
שעד עכשיו דיברנו עליו, בגלל שהפוק הזה, ומה התכוונת? איך אמרת שהוא שונה?
מה אמרתי לך בשלב ההפסקה? דובר על זה שנתום ההפסקה, הרגע המצטייק. כרגע אני רק השתמשתי בו בשביל להניח את בשביל לעשות את המין-פילד אפרוקסימיישן, הנחתי שהוא קיים, עדיין לא אמרתי מה.
אנחנו לא רואים כמו בלנו.
בינתיים.
שמעת שכאילו לכל K-up יש ספין אפ ולכל K-down יש ספין דאון?
מה?
שמעת שלכל K-up יש
אמרתי, שים לב, K חיובי, זאת אומרת חיובי הולך עם אפ, K עם סימן שלילי הולך פה עם דאון.
כן.
זה שאתה.
איך אני מסתדר? הייתי עם ריבוע שזה יוצא רק כאילו גם את האיבר באמצע של השתיים כאילו רגע
אני מלא את EK בריבוע, אז אמרתי איבר כאילו כזה קוסינוס כפסינוס
את זה בריבוע ועוד זה אני מוסיף 0 יהיה לך פה איזשהו, יש איזה יחס בין הקוסינוס לאפסילונים שהוא מוסתר קצת, עובדה שקיימים פה ומעצבנים. ואני מוסיף את זה בריבוע. כמובן יש מיליון דרכים לפתור את זה, אתה יכול להסתכל על משוואה אחת, לפתור אותה עד הסוף, ואז להכניס את זה בשנייה אם אתה רוצה. יש כל מיני דרכים שאפשר להשתמש בהם. כמובן, סקור של דלתא ואפסילון, אנחנו מניחים שהם פשוט גבוהים שלומדים אותם. בעצם יש לך פה שתי משוואות שמסנן תכלס נעלם אחד, שזה הטטרה, אבל אנחנו רוצים את האנרגיה.
הדבר הזה הוא תלוי K, הוא לא יכול להיות קבוע. אז אם הוא תלוי K, אז איך בדיוק הגדרנו אותו להיות קבוע בדיוק?
הוא קבוע לכל K.
אוקיי, הוא קבוע לכל K לחוד, וגם זה בעצם קבוע לכל K לחוד.
לא, זה קבוע כללי.
זה קבוע כללי?
כי זה פה יש לך סכימה על כל ה-K.
אוקיי, כן, צודק. זה הגדרנו את זה על סכימה על כל K. אוקיי, סבבה. עכשיו, פה. המעבר מכאן לכאן. עכשיו, הבנתי שאת המינוס הזה אתה דוחף לפה כדי להפוך אותו לפלוס. נכון? עכשיו, היחס הזה שפה. עכשיו, כשאני עושה אנטי קומוטציה, נכון? יש פה אולי אמרת, איך אפשר מקסימום לחוק את זה? אז אם אני רוצה לרשום, נגיד לצורך העניין, את CK תג דגר, אנחנו יודעים שזה לצורך העניין שווה ל-CK תג דגר, פלוס CK תג דגר, CK, שזה צריך להיות שווה לדלתא K דגר, ממה שאנחנו מכירים. עכשיו, אם ככה, אם אני רוצה להחליף עכשיו את הדבר הזה לצורך העניין, נכון? אז בהנחה בשני אלו, אז בהנחה וזה קורה, רגע, לא, אתה יודע מה? לא, אתה צודק, את הביטוי הזה צריך להיות שווה באמת בדיוק להפוך כזה, פשוט לחסוך כל כך חיבור, אז פשוט הצבת את זה ישר. נכון? זה מה שעשית. אוקיי, אני סתם נכנסתי לעצמי לזה. עכשיו, מה עשינו פה בשלב 3?
סער.
מה?
זה חלק אני פשוט שכחתי לצלם, זה חלק מהתרגול.
זה?
כן, מה שזה...
כן, כן, אנחנו גם נדבר על זה.
אוקיי.
עכשיו, אתה רוצה לחכות קצת, אז תהיה את כל הגרפים שם, כי אני רוצה לשאול את הגרפים קצת.
אוקיי.
It's gonna be fun, it's gonna be
לגבי 3, למה עשינו את זה? מה אני צריך חישוב את זה? זה לא כאילו שזה עצמאי.
בעיקרון עשיתי את 3 קצת הפוך. במקום לקחת את הטרנספוז של המטריצת U ולראות שזה שווה ל1, אני פשוט פתרתי את המשוואה שתביאו את הערכים ההפוכים.
אוקיי, אבל למה אנחנו צריכים לבדוק את התנאי הזה? אבל אמרת שאנחנו צריכים לבדוק רק שני תנאים לצורך העניין. אז הנה, בדקתי עוד תנאי 2.
אני רוצה לבדוק בכלי שהתצומציה היא נכונה.
כאילו אתה רצית לוודא את עצמך כאילו לצורך העניין? שזה מתוצאת תנאי שמתקיים כברירת מחדל כביכול?
זה וגם כן בתרגול עושים אקסטרה.
אוקיי, אז כאילו נוספים את התנאי השלישי סתם. אז כאילו...
לא מתקרב. מה, אתה יכול לעשות את כל החישוב הזה הרבה יותר קצר ממה שעשיתי. בזה שאתה פשוט פותר את המשוואה, הרי ש-U דאגל שווה ל1, אז אתה פותר את זה.
אז רגע, אז למה עשית את השורה הראשונה? או למה זה זר? אתה אחד קצת פה. למה עשית את השורה הזאת? זאת. אז כן, אבל אני לוקחת את חלת לשנינו ודאגת להציע פה.
זה נובע מהשורה הזאת.
אוקיי, וזה נובע מהשורה הזו, מכיוון שכאילו אתה...
UK בריבוע ועוד VK בריבוע שווה ל1.
כן, ואז יש לך אחד השלט זה ואת זה, יש לך את שנינו שפה לצורך העניין עכשיו.
אני אספר לך פה UK.
ספר UK? אני אוסיף UK. כיוון מה כאילו אתה עושה עם זה שיש לך, כאילו שנינו הולכים ביחד.
VK UK, VK UK.
כן, שנינו ילכו, ואז אני שאלתי שנינו שאתה יודע שזה וזה סימות אחד, ואז אגב שוויון בין הדבר הזה, ובין הדבר הזה ש... לא, זה ברור
CK.
כן, זה שוויון בעצם בין ה-C, נכון, שני הדברים עם CK צריך בעצם לפודד את זה בעצם. אתה בעצם רוצה להציב, נכון, אתה בעצם מציב את גם K ואת גם מינוס K, ואז אתה מקבל את זה. ואז אתה מפעל את CK ואז אתה עושה עצמך ויקבל את זה, ואז אתה הולך למטריצה הזו שפה. עכשיו, למה היית אבל צריך שנינו של המטריצה?
זה פשוט מטריצה חלופית. זה ליטרלי מטריצה חלופית. זה עובר מגמא ל-C.
אוקיי, אתה בעצם מתייחס פה למטריצה U כפול הגמא הזה, נותן לך את מטריצה כתב, ואז הוא...
טאק, כפול וקטור גמא.
U טאק כפול וקטור גמא ייתן לך את ה-CK האלה, ואז זה מה שעשית בעצם. נכון? אז אתה U טאק כפול גמא, וזה בעצם, זה ההחלט עצמה, את הכל, נכון? אומרת, זו הייתה המעצת המקורית שהכפלת אותו וגם ב-NC, ואז אמרת ההופכית שהקלטה שלך צריכה להיות גם כן, לראות כמה פעם אחרי השיתוף הצבעה, וראית שזה בעצם נמצא במעצת היחידה, ואז רשמת את כל הממתני הקולה, שזה היה כל מה ששם, הצלחת לסדר את זה בצורה הזו ונחסנת אותו בפנים. ואז רשמת למה הדבר הזה, נכון? מה?
דלטה, זה משהו יוצא בסוף, זה החישוב שלו.
אוקיי, סבבה, אני אעשה את זה, תודה.
Sir,
Yes, hello.
in UK and UK, you from where you substituted the rightmost
This one?
square, yes.
Basically solving here. If you solve it all the way down, you get the theta k.
Yes.
You can put it back in. Theta k will be like
Okay.
tangent to the power minus 1 or something. Something.
I understand. So you substituted for theta k.
Also, you can open another method. The thing might be simpler is opening the cosine and the sine with the cosine elation. What?
אתה יכול למחוק רק את החלק שלא קשור לתרגול.
זה?
שלא הבנת. הם יחתכו את ההקלטה וזה.
Okay, so 5 minutes. Any questions before we start again?
רק פה צריך להיות ציון, נכון?
כן.
שלחתי לך הודעה לגבי התרגולים והרשימות שלך, נראה לי שלא כל כך הבנת אותי.
זה שהראית את הרשימות בכתב, כן?
את הרשימות בכתב ואת ההערות שלך, שאתה כותב יודקה. שתי הדברים האלה, כן.
בדרך כלל, לפני שאני מעלה את הטקסט של יודקה, אני מסיים דברים שלא נראים לי חשובים שאני מוסיף על זה. בכל מקרה אני אעלה את כל... אני אשים עוד כזה סקשן של פרסונל נוטס ואני אעלה שם את כל הנוטס שלי.
אוקיי.
טובים, אבל מצד שני צריך לעבור עליהם לראות שונה טעויות. אוקיי.
רגע, ושנייה, אז אתה תוסיף את זה כאילו בסוף או כאילו... בסוף סמסטר תוסיף את זה או שכאילו את כל המחברת שלך?
לא, אני אשים את זה הסופה של כמה דברים שצריך להכין לשני קורסים ואז אני אעלה את זה מתי שאני אספיק.
כן, אבל לא רק של ה...
כל התרגולים אני אעלה את המוצאים.
כל התרגולים, גם של התרגול הראשון, כי שם...
למרות שכנראה לא יהיה, אין לי נוטס על פאף אינטגרל, נוטס אישיים, כי ריצ'רד לא לימד פאף אינטגרל, אז אין לי את זה, לא הכנתי את זה.
שאלה אחת, איך הוכחנו בסוף שתנאי 3 מתקיים בפועל, כאילו הוכחנו שזאת יחידה או שזה פשוט מישהו ששאלת לנו לעשות?
איפה? 3?
כן, בסוף 3, ממש
זה הוכחה מזה ש... אוקיי. The transformation is unitary because we saw that the reverse transformation is just the complex conjugate of the original transformation.
כאילו, אתה אומר שברגע אנחנו מצאנו פשוט את המצצה המקורית, נכון? את היו המקורית, ולא מצאנו אותה, ואז אמרנו שפשוט שאף שחלוף הצמדה. ואז מזה אמרנו שאם נכפיל אותה נקבל את מצצת היחידה, באמת, אם נעשה את החישוב.
This one, just look. This one give us the gamma vector.
כן.
This one will bring us back to C. So this one, by definition, has to be 1.
Okay.
We didn't do anything.
זאת אומרת, אתה לא הוכחת שזה יוצא אחד, זאת הנקודה שלנו.
Yeah, I didn't calculate
זאת אומרת, אם אנחנו יכולים להמשיך את החישוב שעשינו שם ולהוכיח שזה צריך מצצת יחיד. זה מה שאתה בעצם אומר.
Now you continue, yeah?
Maybe. Probably. Yes. Get off the phone. Okay, let me just see if I need to see if I want to see anything else before I write the graphs. No, let's write the graph and then talk about it. First graph I want to write is this where the x-axis is epsilon k, and the y-axis is ek. This graph will look like, oh, wow, it's even better than I thought. This here is that. This will give us a gap from our zero energy ground state to our first excited state. A gap here, which basically means that if we have some temperature. I'm going back to thermodynamics a little bit. If we have energy from temperature, which would be kBT in some material, again, remember this. All of this is like the background of a superconductor. So if I have a metal with some temperature, the perturbation energy in it will be equal to kBT. And if kBT will be lower than its delta, we'll get a stable state that cannot jump up to its excited state. And in the paper that I'm gonna add, it will show that this condition shows us superconductivity. The way that we can think about it simply is that I'll keep this graph around. We'll talk about the vacuum state of this Hamiltonian, and then I'll go back and explain why the ground state looks like superconductivity. Just a little bit. Again, I'm not going to prove it or go too deep into it. Again, above my paycheck.
Is this related to like a valence bond and conduction bond also?
What did you say?
This represents also similarity with valence.
Are you reading Wikipedia to me?
No. I attended some talks and and I found a similar diagram. So I captured a photograph.
I think so, but I'm not very good at studies in the.
It was optics talk.
It was an optics talk. Oh yeah. Now I'm embarrassed. Now I'm truly embarrassed.
It represents the excite on the whole and pair, right?
Yeah. We'll talk in a second about the copper pairs.
Yeah, it's the same. Yes, valence and excite conduction bond.
Yeah, it's the same. Yeah. And the second graph that I want to show you is this one. The y-axis has no units. The x-axis, again, okay. See that VK, we go for VK. Right. This will be a graph of UK. Also, if you compare, we know that if we add UK squared plus VK squared, we get 1. So VK squared, VK squared equal to 1 minus V squared. And we'll see in a second that UK will represent the amount of copper pairs that we have, and VK will represent the holes. We'll see it after we talk about, again, the BCS vacuums. So now I'm erasing the right side of the board. There. our vacuum state, our BCS vacuum state, will be defined by gamma k BCS equals to 0. And in your homework, again, my favorite phrase, thank you, you will prove that BCS vacuum is equal to, this is a sum, a multiplication, the product of UK.
Okay, it's product of K.
Yeah, product of K. I'll do it a little bit. It's VK, CK dagger, C minus K dagger. You will also prove, you also show in your homework that there's another representation for the BCS ground state. Right? So we see here that it's a combination of many populated Fock state, pairs of populated Fock state, and vacuum states with it. So we see here like 2 electrons in the what we call the Cooper pairs and holes interact with each other. Right? So let's, instead of finding this, which you'll do in your homework, I'm gonna prove some condition that must be. First condition is that equal to 1, orthonormal. So let's open this up a little bit. Cool. I can take the BCS for each K, so I can also write it as the product of K, what I call BCS K. And then this cross product here, this product here, will just be BCS K equals K infinity. Two. Right? And now, if I prove this multiplication is equal to 1, I'm basically done. Because if for k equals 1, it's 1, so for k equals 2, it's also be 1, and so on and so forth. Alright, so in general, BCS k equal to 0. UK, it's supposed to be UK conjugate, but again, UK is real, so it's just UK plus VK. Okay. UK plus VK minus K, CK dagger, C minus K dagger, 0. U times U will just give us a constant, so it will be UK squared. UK times VK, CK dagger, C minus K dagger will zero out, since it will no longer be orthonormal to 2 sides, the bracket, and VK. So you just have the term VK times vk here plus 0 vk squared c minus k ck dagger c minus k dagger. Using weak theorem, came back. You'll see that the only fully conjugated term would be this one. With this one, overall it will be equal to uk squared plus vk squared. So 1. Very good. So first condition for it. You want to also take a picture of the other side because I'm pretty sure I'm going to erase that side and not this side.
שאת השורה הזו, לא את השורה הזו.
אני מחכה כל הזמן. לא אכפת לי, אני רוצה לשאיר את הגרף שלי. Second, I don't want to do this. Second thing that you need to do is calculate gamma PCS. This needs to be 0. Right? I'm pretty sure it's in your homework, but let's do it anyway. You know what? No, it's in your homework. Why should I do this? It's in your homework. Let's instead, this one. I proved it. Look. Right. Next, let's find the mean number of electrons. Yeah.
יש לך פה אבל יותר מ-full conjugated איבר אחד, שני איברים כאלה.
Well.
יותר, אז למה אחד כזה?
Well, which one?
הרי יש לך נגיד לצורך העניין את הראשון עם השני ואת השלישי עם הרביעי.
ראשון עם השני, first with the second?
כן, ואז זה אפס, נכון?
This is 0.
ואז גם יש את הראשון ואת הראשון עוברים לראש שהתייחסת. עכשיו מה עם הראשון והשלישי ואת השני ועם הרביעי?
What's the commutation relation between C minus K and CK dagger?
הם אמורים להיות חלופים כמאינדקסים שונים, נכון?
0.
K שווה, רגע, K בכך שונה מ-X?
We didn't think about K equals 0, but we can assume that our electrons are standing still. I think it's a good assumption.
אוקיי, אז בעצם הגורם היחיד ששווה להתאפס זה הגורמים האלה שעשית פה, נכון?
Yeah. You can check it yourself. Okay, so we want to find the mean BCS in CK dagger CK. Yeah. All right. I can plug in the BCS using our normal vacuum, but this will give us this, which is very ugly. It's very long and ugly. Ew. Or I can take the C and plug the gammas in our operators. Same way as we can work in the Schrödinger representation of the Heisenberg. Okay. It's a minus in one of them. It's not in my notes. Let's see. Which one is a minus? And it can fold that. This one has a minus here. I knew it. Okay. Squared of gamma. Okay. Okay. I'm not going to write these two terms, but minus vk times uk and uk times vk. Those two are supposed to cancel out. Okay. Oh no. If we multiply these cross terms, when I get two annihilation operators, 0. Those two creation operators, again, cut them out. So we'll also have the minus
creation of different k. Creations of different k and minus k. So why you would do 0?
Yeah. Well, it's dead. Oh no. Okay. You can go on.
Because gamma and gamma
Yeah.
operating on BCS.
I also have another mistake here. So I can also minus. It will be a plus squared. Okay, now minus k. Equal to. You can clearly see that this term vanishes because you found this condition. Huh? You found this. It's good. You did this. Vk squared. So Vk will be a representation of the number of pairs that we have, and the Uk will be the number of holes.
איך אנחנו נקרא לזה שזה מספר הזה? אוקיי, זה עובד יצירה והשכנה.
This one is Vk.
אוקיי.
Alright.
אתה אומר שאתה בדק פה, זה רוצה אותו מספר, פשוט שמספר חלקיקים שפתח, אז במה מספר חומרים. זה אופרטור של מספר חלקיקים, זה יכול להיות מספר אלקטרונים, לא מספר אפורים.
This is the number of electron pairs. U is the number of holes.
רגע, אבל זה לא מספר
The
אלקטרונים
ratio,
בדי.
it's
כאילו, זה לא מספר של אלקטרונים, לא זוגות אלקטרונים, כאילו, זה ממש כמו אותו מספר של K, לצורך העניין. זה לא נגיד אופרטור של K סקיוס K או משהו.
and notice when I create in K, I also create a minus K.
זה בעצם כשבודק מספר מבוקד, אני בודק.
Yeah, now we have.
Sir, what happened to gamma with BK square and multiplied by gamma dagger?
This one?
BK square, yes. You wrote just BK square and
Gamma
inner product
dagger?
of BCS. That would be 1. And what happened to gamma dagger?
This one. Gamma dagger. You create a quasi-particle in your BCS. Again, remember, those gammas are like an annihilation creation operator on our normal Fock states, but with some BCS something, right? So I'm not explicitly saying what gamma dagger BCS equals to. Just saying you create and annihilate. And because it's a fermion, I can assume that the constant that comes out of this creation will be 1 overall.
היא אמרה בהרצאה שזה הסתברויות, K ו-K, ואיך מוחלט בריבוע.
Yeah.
אז איך אתה רואה פה את העניין של ההסתברות?
I erased the value of Vk, but if I remember correctly, Vk is the square root of 1/2, 1 minus, I think it's Ek. epsilon k. Right? Where ek, oh no, it's the other one. It's the other one. It's epsilon k. Yeah, it's the other one. Ek is bigger than epsilon, so this is a square root of something that is smaller than 1. So it is the ratio. Thank you for checking.
אבל יש חצי נוסף שאתה מכפיל פה כאן. החצי הזה הנוסף הזה זה כאילו מה שאנחנו לא נהיה מעל 1 אף פעם. מה החצי?
It's ratios, so that's it. It's ratio between copper pairs and holes.
כאילו אבל זה אומר שסיכוי לקופר פרס לא יעלה מהחצי בעצם, נכון?
This small epsilon can be minus.
אוקיי, זה כאילו מגדיר אותו ביחס לאנרגיה חיצונית וכל זה?
Yeah, I can yeah. It's something that I skipped from in the beginning because it's very annoying to justify the change in the Fermi state. But you can see it's the same here. If you assume that your zero state is in the that your epsilon is antisymmetrical around 0. It has minus plus.
כאילו פשוט זה אני פרמי, אז זה יכול גם להיות שלילי לצורך העניין, ואז כאילו זה יכול להיות יותר גבוה.
It's up to the Fermi. Yeah, I'm taking it relative to the Fermi C. No, that's. And that's it. It's also 7.5, and we basically finished everything. There's one more equation that we're supposed to do, and I forgot it. It's there. So I'll send the notes. The notes also have a lot more material in there, and and this weekend all my handwritten notes will also be uploaded. We'll also have some extra stuff in there. Yeah, I just want to go through them once more to check it for sure there's no mistakes or something. And that's it. And you'll get homework, big homework. Yeah, it's going to be big homework, but you basically can send it to me like up to a week before the exam. So there's like, take as much time as you want. If I can put in the Moodle no date, submission date, final submission date, I'll do it. So just going to be homework to do sometime before the test.
And there will
Test
be
me.
one more.
It's last.
It's last homework, but it's going to be about the BCS and path integral, which we'll do next tutorial.
There will be
So
next week or so?
next week.
Next week, yeah. Next week, next tutorial, and then the week after that, it's already finished. Done. There's no semester anymore. No more school. באיזה יום נגמר הסמסטר?
19 ביולי.
מתי? באיזה יום זה יוצא?
יום שישי.
שישי?
איך אתה מסיים 18?
No, I just wanted to I just asked you what date is when the last day of the